So the topic of today's lecture is indicated on this green board, statics and dynamics of rigid bodies. First, I will remind you the definition of the angle of rotation and angular velocity and angular acceleration. If a material point A is engaged in a circular motion around point O, and the radius of its trajectory, circular trajectories R, then in some time period, this point will move from one point to another point on the circular trajectory. So this displacement of material point takes certain time interval delta t, and the displacement itself is delta s. That is the length of the arc defined by the central angle alpha. The angle alpha is by definition equal to S divided by R. That is the length of the arc and the radius of the circle. That is the radian measure of angle. Angular velocity is the rate of change of angle alpha with time. The rate of change. So this will be according to this definition 1 divided by R delta S over delta T. Delta S divided by delta T is the average velocity of the point on this interval. So that will be the velocity divided by radius R. From here we can find the velocity if we know the angular velocity. That will be angular velocity times radius. Also angular acceleration is defined as the change in angular velocity that occurred during some period of time delta t. And that will be according to this formula. That will be an delta v, the linear velocity or tangential velocity in this trajectory divided by delta t 1 over r, which is a linear acceleration over r. So linear acceleration will be angular acceleration times radius. I just remind you these physical quantities well known from kinematics of circular motion. Now the definition of angular velocity is very similar to the definition of linear velocity. In linear velocity we have delta S over delta t, and here we have delta alpha over delta t. In linear velocity we have the rate of change of the displacement of material point. In angular velocity we have the rate of change of the angle through which the material point has traveled. during the time interval delta t. And in the same way, angular acceleration is very similar. The definition of angular acceleration is very similar to the definition of linear acceleration. In linear acceleration, we have that linear acceleration equals the rate of change of linear velocity, or linear speed. And here we have the rate of change of angular velocity. So as the definitions are the same, it means that most of formulas are the same. Most of formulas. I will probably show some of the formulas here, which are absolutely equivalent, absolutely looking like formulas for circular motion look like the formulas for linear motion. So in linear motion, we have the displacement is the initial coordinate plus velocity times t. In circular motion, we have the angle through which the point has turned about the center equals the initial angle plus angular velocity t. If there is uniform acceleration, then the velocity in linear motion equals the initial velocity plus acceleration by time. And in circular motion, we have angular velocity is the initial angular velocity plus angular acceleration by t. And for example, the displacement in case of uniform acceleration is the initial coordinate plus vt plus at squared over 2. For circular motion, the displacement will be angle alpha, initial coordinate, that will be initial angle, then velocity times velocity by time is angular velocity time plus angular acceleration times squared over 2. So all the formulas are absolutely identical. The kinematics formulas for kinematics of circular motion are identical to the formulas of kinematics of linear translational motion. So next we consider some solid body or rigid body which can rotate about the axis which goes through the point A, and the axis is perpendicular to this board. So the axis is directed here, and the body can rotate somehow about this axis with angular velocity omega. What will be the kinetic energy of this motion? Certainly some kinetic energy must be present here because each elementary mass has its own velocity. And if we indicate here some mass point, which is for example m1, it will have velocity v1, and it will have distance from the axis of rotation by some radius vector r1. And so the kinetic energy of this mass will be m1, its velocity squared over 2. If we consider another point, m2, it will have its own radius and its own velocity v2, and it also will give its impact to the total kinetic energy. It will be m2 v2 squared over 2, etc. We can divide this body into many elementary points, and each point will have its own kinetic energy. As many parts in this solid body we choose, then the same number of terms will be in this sum, indicating the kinetic energy of the rotating rigid body. Velocity of any point can be expressed through the radius vector, its radius vector of this point, and the angular velocity of rotation of the whole body. So this may be written as m1 over 2, and velocity will be its radius vector squared omega squared plus m2 over 2 radius vector 2 squared omega squared, etc. The number of terms will correspond to the number of points in this rigid body. Angular velocity is the same coefficient. It's the same number for all the points of the rigid body. The same angular velocity is a part of each term here. So angular velocity can be taken out of the round brackets, and we will have angular velocity squared over 2, and inside the brackets what will remain here, m1 radius vector 1 squared plus m2 radius vector r2 squared plus etc. This round bracket is called moment of inertia. So this is a moment of inertia of the rigid body. So the final formula will be moment of inertia times omega squared over 2. That will be a kinetic energy of rotating rigid body if it rotates with angular velocity omega, and if the body is actually rigid, that is non-deformable. If it's deformable, if it's like made of rubber and different parts of this body can be displaced relative to one another, then different parts may have different velocities which will not satisfy this equation. If different parts are somehow moving with respect to each other, if this body is made up of rubber, for example, then this will be not true for different points. The velocities will be defined differently, and then in this case this formula will not work. This formula will give incorrect result. So this formula applies only to actually rigid bodies which are non-deformable, which are non-stretchable. This physical quantity, moment of inertia, plays the role of mass for a mechanical translation of mechanical motion. In translational motion, kinetic energy is mv squared over 2. In rotational motion, kinetic energy is, as we have shown, moment of inertia omega squared over 2. So instead of linear velocity, translational velocity, we have angular velocity here, and instead of mass, we have moment of inertia. So moment of inertia corresponds to inertial properties, describes the inertial properties of rotating body. And this quantity depends on the distribution of masses, because here we have a path along with masses of each point. We have a distance of this mass. We have distance of this mass from a distance from the axis of rotation. So if all the masses are very close to the axis of rotation, then all the distances, all the radius vectors will be small quantities, and the moment of inertia will be small. If all the masses are far away from the point O from the axis of rotation, then all these quantities R1, R2, etc. will be large quantities, and taken squared, they will give a large moment of inertia. So moment of inertia depends not only on the mass, but also on the distribution of mass inside the body. Now some examples of the moment of inertia. Suppose we have a hoop of radius r and mass m, and all the mass is distributed evenly along this circular body, along the circle, which is the hoop of radius r. So the center is empty, and all the mass is distributed at this line. In this case, every mass element will be at the same distance from the center, at the same distance. All the mass elements will be at the same distance. So the moment of inertia will be equal to total mass radius squared, radius of this hoop. Now suppose we have such a wheel which is of radius r, but the mass distributed inside this volume, and there is an external radius and internal radius small r. And all the mass m is distributed in this area. Well, if the mass was all distributed along the larger circle of radius r, then the moment of inertia would be m capital R squared. If all the mass was distributed along the smaller circle, then the moment of inertia would be the same mass times small r squared. But in this case, the mass is distributed somehow between these two radii. So in between the small radius and large radius, all the mass is somehow distributed in between. So the resulting moment of inertia must be somewhat in the middle between these two numbers. It must be something like E1 plus I1 plus I2 over 2. So maybe we can expect it to be m capital R squared lowercase r squared over 2. This formula turns out to be correct because if you derive it accurately, you will obtain this formula. It's obvious from intuitive approach that the resulting moment of inertia must be something like the average, the mean between the two moments of inertia. And the resulting formula appears to be correct. Even if you derive it accurately using calculus. Now imagine another body of radius r such that the mass is distributed evenly over this cylinder. The mass m. This body can be considered as the limiting case of the previous body with the small radius tending to 0. If the small radius goes to 0, then this body will tend to coincide with such cylinder. And therefore the moment of inertia of this cylinder can be obtained from the moment of inertia of this formula when small r is 0. So it will be mr squared over 2. The small radius is 0 in this case. Well, enough for moments of inertia. We will probably calculate more moments of inertia of other bodies next time. But now we will consider another question, which is dynamics of rigid body. That is dynamics of rigid body. Let's there be a point mass m which can rotate about the center O, and which is located at distance r from the center, and so it can move with some velocity along the circular trajectory about this point A. And let's consider a force, arbitrary force acting on this mass. If the mass is rigidly connected with the axis of rotation, that is, here is some rod which is unstretchable, which cannot be deformed, so that the length of this rod is always the same. It doesn't change in time, and it's equal to r. Only the mass and the rod is massless, and all the mass is concentrated on the end of this rod. Then in this case, what will happen if force F with arbitrary direction is acting on this mass? It's clear that the component of the force directed along its radius, along the radius r, this component, which I will call parallel component, parallel to the radius. This component of the force can do nothing with this point. It cannot change the motion. It cannot change the velocity. It could have caused some deformation of the rod, but we assume that the rod is unstretchable. It cannot be deformed. It cannot be elongated. So the force F parallel cannot change the motion. Cannot influence the motion of this point. But the parallel component of the force, this one, the perpendicular component, perpendicular to the radius, will certainly change the motion. It will cause the mass to be accelerated. According to the second Newton's law, this force F perpendicular, which is perpendicular to the radius, can change the velocity, the tangential velocity of this point, according to Newton's second law. And we know that the acceleration of the body can be expressed through its angular acceleration if this body is engaged in circular motion. So it will be angular mass times angular acceleration radius r, according to this formula. So only the component of the force perpendicular to the radius can change the velocity and cause acceleration. But the component parallel to the radius will not influence the motion of this point. It can be disregarded in this particular problem. Let us multiply this equation by radius r. So we will have force perpendicular component times r will equal to m r squared angular acceleration. Why this formula is good? Because it includes mr squared, which is by definition a moment of inertia of this material point. Moment of inertia, which characterizes the circular motion, the inertial properties of rotating body, and along with the moment of inertia we have angular acceleration, which also refers to rotational motion. So in this formula, after we multiply the second Newton's law by radius r, we obtain in the right-hand side of this equation all the quantities which are related to rotational motion. So this quantity must also be of importance, and this is usually denoted by m, and this is called a torque. A torque of force F. So this equation can be written as, I will do it here, for rotational motion, the torque acting on a body equals its moment of inertia times angular acceleration. And the equivalent, the corresponding formula for translational motion is the force equals ma, mass times acceleration. That is the second Newton's law for translational motion. Force equals mass times acceleration. And here for rotational motion, instead of the force we have torque. And instead of mass we have a moment of inertia. And instead of linear acceleration we have angular acceleration. Let's continue the line along which the force is acting. And let's draw a distance, perpendicular section from the axis of rotation to this line, so that this angle is the right angle. And let's denote this section as h. This is very useful because if we know this angle, alpha, then the force perpendicular component of the force will be equal to the magnitude of the acting force times cosine alpha. And so the torque, which is by definition equal to a perpendicular component times radius, and we use this equation, equation for perpendicular force, so it will be F times r cosine alpha. And what is r cosine alpha? This is r, and angle alpha is here. This angle equals this angle, because one leg of this right triangle is perpendicular to this side of this right triangle, and another leg perpendicular. It's very by the construction of this picture, we know that this angle equals to this angle. And so in this right triangle, this is the angle phi, and this is the angle phi, and another angle of the right triangle should be alpha. Inevitably, it should be the same angle. So here is alpha, and so H equals R cosine alpha. What we have here, this is H. So that the torque M may be expressed in two different ways. We may take a component of the force acting on the body perpendicular to the radius r, a component perpendicular to the radius, times radius. Or we can take the magnitude of the force, not its component, but the total magnitude of the force acting on the body, times h, and h is the section perpendicular to the line of action of this force. H is called the lever arm. H is called lever arm, or simply the arm of the force. So this might be called the arm of the force F acting on the body. H is the arm of the force F, or it's sometimes called a lever arm. Both presentations of the torque are very useful. In some problems, it's more convenient to calculate the torque as the perpendicular component of the force times radius. And in other problems, it's useful, it's convenient to represent the force as the force itself, its magnitude, times the arm of the force. So we have obtained a equation which is the second Newton's law for rotational motion, which looks similar to the second Newton's law of translational motion. But it includes only the quantities related to rotational motion. Every quantity included in this formula relates to rotation, while here every quantity relates to translational motion. Well, let's consider a small problem. After so many formulas, we will consider a small problem. Let's say be a slope an inclined surface and a disk or a cylinder with uniform distribution of mass m and radius r, and this solid cylinder rolls down the inclined surface. So it rolls down with some acceleration a. If there is no slipping, if forces of friction are enough to exclude slipping, then this cylinder will roll down, and we have to find acceleration a with which the cylinder will go down the slope. So in some time interval, the cylinder will be found somewhere here, so that it will be displaced by some distance delta s, and the center of mass of the cylinder will go down from some initial position to a final position by some height delta h. And the cylinder, if it starts from zero velocity, it will have some velocity here, it will have some final velocity, and it will be rotating at some angular velocity, which is obvious. We are not solving the problem, we are just analyzing it. That is the first step in solution of any problem. Whenever you have a problem, first step you have to make is to analyze the problem. To analyze, what does it mean? It means to draw a picture, to make such a sketch of what is going on in this problem, and to analyze and to understand everything about velocities and angular velocities. Yes, what's the question?
The acceleration going downward, right?
Yes, acceleration. Acceleration of free fall is always directed downward to the center of the planet. So there is certainly some force of gravity mg, yes, it's directed downward to the center of the Earth. But the cylinder cannot fall down through the surface. The surface is considered to be rigid. So the cylinder has to roll down along the surface, and acceleration of its center of mass will be directed parallel to the surface. Why so? Because we believe the surface is rigid enough not to be broken by this cylinder, not to be broken. So what I've done, I've just analyzed the problem. To analyze means to draw a sketch and understand what's going on and probably indicate the initial position of the body and the final position over some period of time, delta t. Over some period of time, this cylinder will be here, will be found here. And we have to understand that the acceleration of the center of mass is directed parallel to the surface, and that the angular velocity will be directed here, it will roll here, and in some period of time it will have some velocity, and the center of mass will go down by some, from some initial position, down from this altitude delta h to its final position, which will be occupied over time interval delta t. And during the same time interval, the point of touch between the cylinder and the surface will be displaced by some distance delta s. So all this is not the solution, it's just the analysis of the problem. And I want to stress and underline again that this is the first step. Analysis of the problem is the first step in solution. If you want to solve, first analyze the problem. Don't rush immediately to write formulas. First analyze the problem. It means understand. To analyze means to understand what's going on in all the details, and to draw a sketch showing everything you have understood. Now, after we have a clear picture of this process, we can write down some formulas. For example, if there is no slipping, then no energy is lost. The energy is lost when you have slipping. But if there is no slipping, no energy is lost. And we assume in this problem that the coefficient of rotational friction of rotational motion is 0. So no slipping and no energy is lost. It means that the mechanical energy is conserved in this problem. There is a conservation of mechanical energy. We can use it here in this problem. So the initial mechanical energy was the initial potential energy on this level. We can assume it to be 0. And the initial potential energy with respect to this point A will not be 0. It will be mg delta h. And the initial kinetic energy is 0 because initial velocity of the cylinder is 0 by the statement of the problem. Initial velocity was 0, and we allowed this problem, this disk on this cylinder to roll down without initial velocity. So initial kinetic energy is 0, but initial potential energy is mg delta h. And the final potential energy, that was the initial, and final potential energy is 0 because we calculate the potential energy starting from this point. And the final kinetic energy will not be 0 because at this position, in this position, the body will be engaged in motion. Its center of mass will have some velocity v, and besides, it will be rolling, it will have some rotational energy with some angular velocity. So the kinetic energy of this body may be calculated in the following way. If we go to the reference frame moving in this direction with velocity v, then in this particular reference frame, the center of mass will be at rest. And the only motion visible will be the rotational motion of this cylinder. In the reference frame moving along this line with velocity v, this will be an inertial reference frame. And in this inertial reference frame, the only motion will be rotational motion, and the only kinetic energy will be omega, will be moment of inertia I, omega squared over 2. In this particular reference frame, which moves with the velocity of the center of mass. Now, if we return to our reference frame connected to the Earth, we will see that along with rotation there is some motion of the center of mass. So there must be some additional kinetic energy associated with the translational motion of this body. By using this formula, I make an assumption that the kinetic energy of a rigid body engaged in complicated motion can be calculated as the kinetic energy of this body calculated with respect to the center of mass, and rotational energy of this body. This is a theorem. This is a theorem called a theorem on the motion of the center of mass. We will prove this theorem next semester, but now we will just take it for granted. The manipulating with the reference frames makes it almost obvious. This formula is almost obvious if you manipulate with the reference frames. One reference frame associated with the surface of the planet or associated with this inclined surface, and another reference frame moving at constant velocity v, so that at this particular moment of time the center of mass of this rotating cylinder will have the same velocity as the velocity of the inertial reference frame. And so at this particular moment of time, this cylinder will be at rest. The center of mass will be at rest. And the only motion in this reference frame will be the rotational motion. At this particular moment of time, after time delta t, after the start of the motion. So this is almost obvious. This must be almost obvious, but accurate derivation of this theorem will be given to you next semester. And now we can just use the relationship between the energies. The initial energy must be equal to the final energy, because the energy is not lost. The mechanical energy is not lost, because there is no friction, no slipping, and no heating of the bodies due to slipping, due to friction. So the initial energy must be equal to final energy. The initial energy is all accumulated in potential energy, because the initial kinetic energy is 0, and final energy is all accumulated in kinetic energy. So that will be I omega squared over 2 mass v squared over 2. And the final potential energy is 0. So what we have here, total initial mechanical energy equals total final mechanical energy. But the initial kinetic energy is 0. We have no term corresponding to kinetic energy. And here in a final potential energy is 0. So we have no, generally we would have some potential energy. But in this particular case, it's 0. Well, we know the relationship between the velocity and the angular velocity. V and omega are related here. And V is the velocity of the center of mass. But if you go to the reference frame moving with this velocity, then this point of the cylinder will have the same velocity in the opposite direction, and all the points of the surface of the cylinder will have the same velocity v, if we go to the reference frame associated with the center of mass. So v will be the velocity of the center of mass with respect to the surface of the Earth, and also v will be the velocity of any point on the surface of this cylinder in the reference frame associated with the center of mass. So v has two different meanings, either the velocity of the center of mass or the velocity of the points of the cylinder in the reference frame associated with the center of mass. But these two velocities are the same, and so velocity v here can be expressed using this formula which we have already indicated. It's omega r, and omega is the same quantity for all the points of this rigid body, because the cylinder is really rigid. It's not deformable. Therefore, all the points will have the same angular velocity. And so what we have from this equation, mg delta h equals I omega square over 2 plus m v squared will give me r squared omega squared over 2. And that will give me omega squared over 2. And in round brackets, I will have moment of inertia I plus mr squared. Also, if the center of mass went down by delta H, then the point of contact was displaced by delta S. And these two quantities are related in certain way. This will be the angle alpha, the same as here. So delta H divided by delta S, delta H divided by delta S will be sine alpha. And so from here we obtain delta S is delta H over sine alpha. Or it's better to find delta H from here. Well, it's obvious. So delta H from here, yes, will be delta S sine alpha. Instead of delta H, I can use this expression, delta S sine alpha. So finally, we can write the following expression. If delta S is substituted here for delta H, then we'll have mg delta S sine alpha. Instead of delta H, I use delta S sine alpha, mg delta S sine equals this expression, omega squared over 2 moment of inertia I plus m r squared. Why do I need delta S? Because delta S is the displacement along the inclined surface, and it must somehow be related to the acceleration along the same surface, acceleration of the center of mass. That's why I need delta S, and delta S will be given by omega squared over 2, and here I will have, well, divided by 2g, and here I will have I over m plus r squared. So if the center of mass was moving at constant acceleration, then the displacement of the center of mass is related to acceleration and final velocity in such a way the displacement is final velocity squared over 2 times acceleration. A well-known formula from kinematics. This formula can be obtained from here. If we take only this term, then the displacement will be equal at squared over 2. When can we use only this term? When the initial velocity is 0, that is just the case in our problem. Initial velocity is 0, and the initial coordinate is 0. That's also true, because I'm counting all the displacements starting from the initial position. So initial position and initial velocity are 0 in our problem. So I can take only this term, and it will be equal to a squared t squared over 2a, and that is v final velocity squared over 2a. A well-known formula from kinematics of uniformly accelerated motion. So if we use this formula here, then that will be v squared over 2a. That's very good, because a, acceleration of the center of mass, that's exactly what I need to find in this problem. The question is, what is the acceleration of the center of mass? I have to find this acceleration. This is my purpose. That's why I'm trying to shape the formulas in such a way that the sought quantity, unknown quantity, can be somehow found from our equations. And the equation we need will be this one, where we can find the unknown quantity acceleration that must be found in this problem. And so we have to make just a few more steps. We have to find acceleration a from here, and also we have to express v using omega, which is a well-known thing. V is related to omega as omega times r. So if we substitute this expression here, omega square will cancel, and we will what remains here will be r squared. And so I can write down the acceleration equal to r squared divided by 2, omega cancelled, r squared, what remains here. So r squared divided by this 2, and divided by what we have here, that will be moment of inertia I divided by m plus r squared, and 2g will go to the denominator. So 2 will cancel, and also we can, it would be convenient to divide both numerator and denominator of this formula by r squared, and what we will finally obtain is g, the acceleration of free form, in the numerator, and in denominator we will have r squared divided by r squared, that is unity, plus moment of inertia divided by m r squared. That seems to be a correct final answer for the acceleration of the center of mass of this cylinder, which rolls down without slipping along the slope, along the inclined surface. What this formula suggests for the motion of such round bodies: if it were not the cylinder but the hoop, all the mass of which is located at the distance r from the center, then the moment of inertia would be equal to mr squared, and the acceleration of the hoop rolling down will be g divided by 2. Something's missing from here. Where is sine alpha? Nobody tells me. I have missed sine alpha. Where is it? Delta S sine alpha was here, sine alpha is here, and sine alpha here is lost, right? It must be in denominator. It must be here, sine alpha, and so it must be here, sine alpha, right? This, yes, and it must be here, sine alpha. No, no, something's wrong. What's wrong in it? Huh? In the numerator. Yes, most probably so. Yes, because it was here. I found A went to the numerator here, and sine went to numerator here. Certainly, sine alpha must be in the numerator. Yes, that's what happens when you lose something and then try to find its proper place. Sine alpha goes to the numerator. Certainly, it must be here. Sure. So that when alpha tends to 0, and the slope tends to be horizontal surface, then the acceleration must be 0. And this formula will give you exactly that. If alpha tends to 0, sine alpha is 0, and acceleration will be 0. But if alpha tends to 90 degrees, and the hoop falls down without slipping, so it falls down and at the same time it's rolling. That happens when the hoop has a sort of thread which is wound on it, and in this particular case the hoop falls down, but it's not a free fall, it's the motion, accelerated motion without slipping, and the inclined surface is vertical, but in this particular case it's a string which is wound on the hoop. Then in this particular case angle alpha will be 90 degrees and sine alpha will be unity, and then the acceleration will be half the acceleration of free fall, because that will be not a free fall of the hoop, but falling and rolling at the same time. That's another limiting case of this problem. However, if this is not a hoop, but a cylinder with uniformly distributed mass, we know that for such a cylinder, moment of inertia is mr squared over 2. And if we use this quantity here, mr squared over 2, then this formula will give us an acceleration of the cylinder will be g sine alpha 1 plus mr squared over 2. Mr squared will cancel, and that will give us 1 over 2. So the final answer will be 2/3 g sine alpha. Yeah, probably this one. So if the mass is uniformly distributed, then the moment of inertia will be different. Which acceleration is larger, acceleration of the hoop or acceleration of the cylinder? Which one is larger? Here we have g sine alpha and g sine alpha. So only this coefficient defines the distribution of mass. Here we had 0.5, and here we have something larger than 0.5. 2/3 is larger than 1 over 2. So the acceleration of the cylinder will be larger than the acceleration of a hoop. Why? Because all the mass of this body, in case of the hoop, is distributed along the surface. And if this is not a hoop but a cylinder, then the mass is distributed evenly. And some parts of this mass are closer to the center. And so this mass which is close to the center will not influence much the motion of this cylinder. And the acceleration will be larger of a cylinder. Acceleration of the cylinder will be larger than the acceleration of the hoop. Any questions? Now let me remind you that what we consider today, the topic we study, the topic we consider is not only dynamics of rigid bodies, but also statics. We have to discuss statics just in a few words. Statics can be derived from dynamics. We have equations of dynamics, that is the dynamics of translational motion and dynamics of rotational motion. Statics of rigid body means that there is no motion. The body is at rest. The velocity is zero and the acceleration is zero. Acceleration of the center of mass must be zero if the rigid body is at rest. And also the angular acceleration is zero. So in the case of statics, this is zero and this is also zero. And we have two conditions. The force, which is actually the net force acting on the rigid body is zero, and total torque acting on the rigid body is also zero. So this is the condition of statics of rigid body. You have to find the vector sum of all forces, and you have to find the torque, total torque acting on the body, which must also be zero so that the body remains in static equilibrium. Let's consider some example. For example, we have a bar with uniform distribution of mass, and the mass is m, and this is the center of mass. And this bar is supported in 2 points. It's supported here and it's supported here. So there are some forces of reaction, some force acting on the bar from the first support, which is F1, and some force of reaction acting on the bar from the second support. And there is another force, certainly the force of gravitational attraction to the center of the Earth. The gravitational attraction is the force applied to the center of mass of the body, and if the body is a uniform bar of length L, for example, total length is L, then in the center of this bar there is this force acting on the bar. And we have to, in order to solve this problem, we have to indicate this distance of the first support from the center of mass. Let it be just half of this section of the bar. So this length will be L over 4. And this length here will be L over 2. The bar is supported in 2 points, and our purpose is to find forces F1 and F2, the forces of reaction acting on the bar. The bar is in the state of rest. The bar is in static equilibrium. And the conditions for static equilibrium are given here. All the forces acting on the bar must be equal 0, the vector sum of all forces. Let's take into account this condition. So the force F1, if it's positive, we may choose it positive or negative, whatever, because it's your choice where to direct the axis showing positive directions. So if F1 is positive, then F2 is also positive, and mg will be negative. That will be the total sum of all forces acting on the bar, and it must be 0 because this is the condition for static equilibrium. And another condition is the total torque acting on the bar. It's convenient to calculate the torque with respect to the center of mass. You can choose any point of rotation. For example, we may assume that the bar is rotating or tends to rotate about this point. We may assume this, and then we can calculate all the torques. Okay, let's do it so. Let it be the point of rotation, the center of rotation 1. Then the torque of force F1 will be 0 because the arm of this force is 0. If force goes through the axis of rotation, then its torque must be 0. Let's calculate the torques of other forces. mg is applied at the distance L/4. That is the arm of this force. And mg tends to rotate the bar in clockwise direction. So I choose it to be positive. If rotation is in clockwise direction, then the torque is positive. And force F2 tends to rotate the bar in counterclockwise direction. So the corresponding torque will be negative. And the torque will be F2 multiplied by the distance from this point of application of this force to the axis of rotation. And the distance is L/2 plus L/4. That is the total torque acting on the bar. Two forces, actually three forces, but the first force is actually has a 0 torque. So we don't take into account the torque of the first force. We take into account only the two forces and two torques. One torque of the weight of the body tends to rotate clockwise in clockwise direction, so it's positive, and another torque tends to rotate the bar in counterclockwise direction, so it's negative. Each torque is the force times the arm of the force. This arm is just L/4, and this arm is given by this round bracket. So this must be 0. We know beforehand because such is the condition for static equilibrium. Total torque is 0. Well, if it's 0, it will be conveniently if I multiply this equation by 4, then I obtain mgl equal F times, if I multiply by 4, that will give me L plus 2L. So that will be 3FL. F2 certainly, what I have here is F2. So L is cancelled from this equation, and what I immediately obtain, F2 will equal to mg/3. The force of reaction here turns out to be just 1/3 of the weight of the bar. Okay, as I know F2, I can immediately find F1 from here. From here, F1 turns out to be mg minus F2, which is mg1 minus 1/3. That will be 2/3 mg. That is another force of reaction exerted by the support in point C1. So I have found all the forces. Force F2 and force F1. All the forces of reaction. I have chosen point C1 as the point of rotation, there is no rotation. The bar is at rest. It's not rotating. But I assume that it can rotate about this point, and all other forces tend to rotate the bar. I assume, in order to calculate the torques. And so I got the solution. I could have chosen some other point as the point of rotation, for example, the center of mass. Then the torques will be different. The torque of mg will be 0, and the torques of these two forces will be non-zero, and they will differ from what I have written here. But the final answer will be the same. The final answer for force F1 and F2 will be the same. You may check it at home. Please do it. Solve this problem, assuming that the center of mass, point C2, is the point of rotation. So the force F1 will tend to rotate the bar clockwise, in clockwise direction, and force F2 will tend to rotate the bar in counterclockwise direction. And if you correctly take into account all the torques, and from similar equation you will obtain the same final result. The final result related to the forces of reaction will not depend on what point you choose, what point of the bar you choose as the point of rotation. We could have chosen this point as the point of rotation, no problem. Or we could have chosen this point or any other point as the point of rotation. And the final result will be the same, because proper conditions, proper physical conditions, and proper equations used to find the forces, and forces do not depend on which point you choose as the point of rotation. That seems to be very simple. I will take another half minute. That seems to be very simple, but actually statics of rigid body is not that simple. And I will give you another problem which has no solution at all. Nobody knows how to solve this problem. The same bar is located in such situation, here is one support, here is the center of mass, and here is another support. And the bar is at some angle alpha to the horizon. Again, here we must have some force of reaction F1, and here we must have some force of reaction F2. And if you try to find forces of reaction F1 and F2 in this problem, you will discover an interesting and unexpected thing. This problem seems to be almost identical to what we have just considered. Just slightly turn the bar and put it on two supports which are not on horizontal line, but one support is a little bit higher than another support. But this problem has no solution. Nobody can solve this problem. Whatever equations you choose, these equations, correct equations, you can use these equations and try to solve this problem, you will not have a solution. The problem is, it's not strictly defined, and the solution is indeterminate. Why? Because forces of friction will be necessary here. What friction is here and what friction is here, and friction is necessary for the bar not to slide down, no slipping down, so there should be some forces of friction. And what is the relationship between these two forces of friction here and here? It's not given in the problem. The problem in such formulation does not include information about friction here in these 2 points. And if you don't consider friction in these 2 points, then the bar will slide down. But if it doesn't slide down, there must be some friction. But what is the relationship between these two frictions? It's not given in the problem. And actually, if you make this situation really and measure these forces, you will find that these forces, each time you put the bar here, these two forces are different. They are variable forces which vary vary randomly, actually. If you put this bar on the two supports once and then repeat it and put this bar on the same supports the second time and then the third time and then many, many times, and each time you measure these forces, they will turn out to be different. The result will not coincide with previous measurements. Each new measurement, each new test or experiment will give you a different result, because this problem is indeterminate. Not enough data to solve such problem. So statics seems to be simple as far as the problems are solvable, but not all the problems in statics can be solved. Some problems are indeterminate. That will be the end of this lecture. Thank you all.